Alright, so we have the following problem. Does the series below converge or diverge? And it is the series starting at n equals 1 to infinity, 1 over the quantity 3 to the n minus n. Now, we have to think of a test to use, right, when we're looking at a series and we're asked to figure out whether it converges or diverges. And yeah, we have a long list of series. There's the tests. You have the geometric series test, and yeah, that wouldn't apply here. It looks like a geometric series, but you have that minus n on the 3 to the n, so no. It's not a telescoping series. I don't think terms are just gonna like cancel out as you write more and more of the partial sums out. I wouldn't want to integrate that, so the integral test, not good. And if you do the divergence test, if you take the limit of 1 over 3n minus n, that would go to 0. And yeah, if it was not 0, then we would say it diverges by the divergence test. So let's look at maybe comparison tests, okay? And I could try out the direct comparison test. And with the direct comparison test, you need to think of an inequality. And the first thing that came to my mind is what I just have written there. 1 over 3n is less than 1 over 3n minus n. So usually when you have a fraction, something with a smaller fraction, the smaller the denominator, the bigger the fraction overall, comparing it to another fraction. So example here, 1 over 3n would be less than 1 over 3 to the n minus n, because 3 to the n minus n, the denominator, is smaller than 1 over 3 to the n. You know, that's kind of like saying 1/5 is less than 1/4. The denominator of 4 is less than the denominator of 5, but overall the fraction is bigger, right? So that inequality holds. But the issue is this. If you looked at the series that we compared 1 over 3 to the n, and of course from 1 to infinity, this converges because it's a geometric series with r less than 1. However, that doesn't help me at all, because what happened here was that the smaller series converged. The comparison test, the direct comparison test, says nothing about that. It only says that if the larger series converges, then the smaller one will. So that didn't help me out. Now, I can think of another inequality. However, that's not always the easiest thing to do. And that's what makes the direct comparison test somewhat challenging. Sometimes you can't find an inequality for which it'll satisfy the conditions of the direct comparison test really easily. So we have another comparison test, which is the limit comparison test. And let's try to use that one. So the limit comparison test says that suppose you have two sequences that are positive, and if the limit as n goes to infinity of the ratio of these sequences is equal to some number p, which is positive, very important, it has to be positive, then both an and bn both converge or diverge. Okay, so I have 1 over 3 to the n minus n, and the way this works is that you're going to compare this to 1 over 3n here, okay? And I'm saying 1 over 3n because, yeah, as n gets really large, the only thing that really matters on that sequence 1 over 3n minus n is that 3 to the n. Yeah, n gets really large, but 3 to the n gets a lot larger, okay? And what we're going to do is we're going to comparably, we're going to look at the series 1 over 3 to the n, or 1/3 to the n, and we're going to ask ourselves, does that converge or diverge? Okay, and that will converge by geometric series criteria, or test, some people call it, because the absolute value of r is 1/3, which is less than 1. Okay, so that's why that would converge, and I will get to that in a minute here, why that we need that. So now I'm going to take the limit as n goes to infinity of 1 over 3 to the n minus n all over 1 over 3, and that's that limit of an over bn part, okay? So we're going to take the limit, and it's always the limit, the thing that goes on top is the sequence of what we're trying to find converges or diverges. and on the bottom, it's the series that we know that converges or diverges. So that's the idea here, is that you compare it to some series that you know converges or diverges easily enough. Okay, and then this is, I think that was okay because 1/3n is just plainly a geometric series. And we're going to take this limit, and I'm going to simplify this limit. Rewrite it this way, because that 1/3n can flip, and this limit would equal the leading term on the numerator or the leading term on the denominator, which is 3 to the n. This would equal just 1, which is positive. Okay, and yeah, you can't say how important it is the order is. Again, the top right here is what you're trying to find out whether the series for that sequence converges or diverges, and the one on the bottom is the one we know something about. Since this limit is positive now, and we know 1/3n converges, and this is where that comes in, that's why it's important, then I can say 1/3 to the n minus n converges as well. Okay, so that's what the test says. If you know one series that whether converges or diverges, and it satisfies the condition where the limit of that ratio of those sequences is positive, then they both must converge or diverge. Okay, so there we go. Oh, and I forgot to write the word converges here, sorry. According, yeah, I would have gotten some points taken off for not writing this out. Okay, so anyways, this test does have some drawbacks. One thing is that often you can pick a series for which you know converges or diverges. When you take the limit, it gives you something like infinity or 0. Okay, and yeah, that's not part of the hypothesis of the test. The test says that your limit has to be positive. Okay, so just look out for that. All right, well, thanks for your time.